So we can look at our energy cost meter here, and we can see that we've got roughly about 434 kilojoules of energy that has been transformed in around 215 seconds. So there's a certain amount of energy that has been used up in that time. That's electrical energy being transformed into heat energy in the kettle. So it's just boiling just now. We've got about, say, 470 kilojoules of energy that has been used up. So that's 470 kilojoules of electrical energy that's been transformed into heat energy to make that water heat. So if we think about the kettle, we've got our wee kettle here. I'm actually going to make it like an old style kettle. There we go.
Oh, that's cute. Looks like a penguin.
Okay, there we go. Penguin kettle. Penguin kettle is plugged into the mains somewhere. Kettle's plugged into the mains over here. Yes. So the kettle's plugged into the mains, and it's transforming the electrical energy that's in that wire there. Electrical energy that flows through the wire is being transformed into heat energy within the kettle. The heat energy will be somewhere in here within that, the wee element that's at the bottom that we've talked about before. The wee element that's here, heating that up. So the amount of energy that is used up depends upon how long it's on for. So the power rating that this particular kettle has was like 2,200 watts. So that basically means that it transforms 2,200 joules of energy from electrical into heat every single second. That's what that means. We'll now go on to look at how power and energy and time are related together through another experiment. So for our first bulb, after 100 seconds for a 16.48 roughly power rating, we've got 1,624 joules of electrical energy being transformed into light and a little bit of heat energy. So for the second bulb, for bulb 2, with a rating of 25.74 watts, roughly, we've got 2,549 joules of energy being used up. So for bulb 3, with a power rating of 34.6-ish, we have an energy usage of 3,462 joules. Let's go on now to calculate the last column there, which is energy divided by time. So as we already discussed at the start, electrical appliances transform energy from electrical energy into other forms. So that can be light, it can be sound, it can be heat. You know, with the kettle at the start, it was obviously heat with the bulbs in that experiment just there. It's light with a little bit of heat. You know, there's going to be some heat produced there as well. They transform energy from electrical energy into other forms. That's something that we kind of know already. How much energy an appliance converts is determined by its power rating. Generally, appliances that generate heat have a higher power rating than other appliances. If you remember back to the kettle, it had 2,200 watts as its power rating, so a very high power rating. When we're looking at the bulbs, though, we're looking at much smaller values. We're looking at 16 or 25 or 30 something, whatever it was. So the experiment that we've just done there with the bulbs should show that the higher the power rating is, the more energy something converts. So that kind of brings us to the next equation. So it's not just a matter of how much energy an appliance converts and its power rating, is to do with the time that it's on for. So the longer you leave something on for, the more energy it converts. So from our experiment we found that power is equal to energy divided by time. The values will be reasonably close. They won't necessarily be exact, but they will be quite close there. So power is equal to energy divided by time. Power, as we know, is in watts. Energy is in that new unit we've been talking about called joules, and time, as always, is in seconds. So we can write this in an equation triangle. In fact, you can tell if I wrote down the right one. Power equals energy divided by time, or energy equals power times time, you could say as well. So P equals E over T. E equals PT. And T equals E over P. So the rearrangement of that equation is the same as we've been looking at before. We've got, I suppose, two new units there. E is energy, and that's in joules, which we write with a capital J. P is power, which is measured in watts. And T is time, and that's measured in seconds. So an example, 100 watt bulb is switched on for 60 seconds. Calculate how much energy is used in this time. So as always in these types of situations, we write down what we are given in the question. So 100 watt bulb is a unit of power. Our letter denoting power in the equation is P. So P is equal to 100 watts. Our time, small t, is 60 seconds. Remember, if that's given in minutes, you have to convert it into seconds. All time in physics is in seconds. And we're looking to calculate energy, which is equivalent to the letter E. So we then would consult our equation triangle, or look in our data booklet. If you look in your data booklet, you'll find one of these equations. But we're looking at energy, we're looking to find out energy. So if we cover up energy, we get power times time. So it's going to be energy equals power times time. E equals PT. So it's going to be 100 times 60. So our answer is going to be 6,000, and our units are joules, which we write with a J. So 6,000 joules of energy is used in that short space of time. That means that 6,000 joules of electrical energy is transformed into light out of the bulb, and a little bit of heat as well.